great numbers of men, a true and equitable method of measuring the use of electricity had to be invented. To this end, many pioneer geniuses turned their talents. Thomas A. Edison contributed the Edison chemical meter. This was a device, a miniature electroplating tank, in which the amount of metal deposited was a measure of the quantity of electricity used. Professor Elihu Thomson contributed the Thomson recording watt meter, which did present a true and equitable means for measuring the quantity of electricity supplied to the consumer. Its introduction put Professor Thomson's company at the head of the parade. However, being at the head of the parade is not enough in the American scheme of things. So the original TRW had to be better. Step by step, as the years went by, it was. 1904 saw the introduction of the Type I, the real predecessor of the modern high-torque watt-hour meter. Then 10 years later came the famous I-14, for which design and manufacturing economies had effected a greatly reduced price. In 1926 came the first of the meters having high accuracy over a long range, the Type I-16, incorporating temperature compensation and low speed. In 1934, the watt-hour meter was redesigned to meet new mounting conditions and, incorporating other improvements, became the Type I-20. Finally, in 1937, came the I-30 with range and accuracy so extended that it was named the General Electric Wide Limit Watt-Hour Meter, a half-century of engineering progress vividly portrayed by the family of performance curves, a half-century of design and manufacturing progress embodied in the trim lines, lightweight and mounting flexibility of the I-30 of today. Now designed with Alnico magnets, the wide limit watt-hour meter of today represents the most efficient and most accurate measuring device in general use. Thousands of these meters are manufactured by skilled workers at West Lynn, Massachusetts. A trip through this plant will show you some of the reasons for the acknowledged excellence of the modern wide limit watt-hour meter. First, you will see gleaming stacks of raw materials, coils of copper, brass, aluminum, and steel. Then the automatic machines that transform the blank stock to thousands, millions of screws and shafts and bolts, and intricately machined small parts, all made to accuracies measured in thousandths of an inch. The clattering rhythm of machine tools. The loud, fast bang, bang, bang of the heading machine blends with the soft, steady drop, drop, drop of finished parts, and the crisp swish of the automatic screw machine as cutting edges slip through a continuous bath of oil to trim tiny flakes from the revolving parts. The part here being made is used in the jewel assembly of the wide limit watt-hour meter. Each of these small pieces corresponds with amazing exactness to other parts from the same machine. Checks for accuracy of cut and perfection of finished item are constantly in progress. In another building, we see strips of silicon steel being placed in an automatic punch press. Vacuum cups pick up each strip and slide it under the press. The waste is thrown out while the punchings themselves march out at the back. Be carefully placed in a box, started on their way to a General Electric controlled atmosphere annealing furnace for a heat treatment which assures uniform electrical characteristics. The curtain of flame prevents air from entering the annealing chamber. It'll be some time before the punchings emerge from the other end of the furnace, so we'll leave them for a while and see what happens to this load of meter frame casting. They too are annealed in a controlled atmosphere furnace. Then they're placed in the jig of this modern manufacturing marvel, the straight line machine. This really is 11 automatic machines, all connected together by an hydraulically operated transfer mechanism which conveys the jig and frame from one machine to the next, stopping for approximately 15 seconds at each station. 75 different tools perform the host of necessary operations. Drills and taps and special cutting tools all function in turn to produce 4 completely machined frames each minute. The back end of the machine is a maze of moving parts. When all operations are completed, the frame is removed from the jig and inspected. And then, at regular intervals, a casting is placed in this multi-gauged instrument, which checks that all machining operations have been carried out to accuracies measured in thousandths of an inch. The frame must be made with great accuracy, so that the parts which are added later will fit exactly. Now to the wheel abrator for a thorough cleaning under a powerful stream of abrasive powder. Here is the frame spick and span and ready for a corrosion-resistant permanent finish. The automatic galvanizer in action. A rack of meter frames dipped slowly into the plating bath. Moves through the bubbling liquid and emerges on the other side with a brand new rust-resistant coating of zinc. The galvanizing is only one part of the permanent finish. Next, the frames are cleaned, and then they are sprayed with a synthetic aluminum lacquer. This completes the frame. And it's placed in an overhead conveyor to begin its trip up to the second floor and the final assembly line. While the frame is on its way upstairs, we'll go back to the element punchings. You remember we saw them being placed in the controlled atmosphere furnace. Here they emerge through another curtain of flame, uniform in every respect. They are to be used in the electrical element, the heart of the watt-hour meter. Another important part of the element is the potential coil, which is layer wound to give minimum potential difference between turns. Notice how the machine automatically places insulation between each layer. The length of the paper layer insulation automatically increases as the coil grows. The current coil is wound of heavy rectangular Formex wire, both ends toward the center, with shellacked insulating strips deftly placed, first one side, then the other, and there's the current coil. Of course, there are many more operations before the coil is finished and ready for installation in the element. In the background, automatic machines perform complicated operations quickly and practically unattended. If you've ever scraped off insulation by the jackknife method, you'll appreciate what this machine does in preparing the lead wires for the electric element. Both ends are cleaned for soldering. Looking across the conveyor belt, we see the ingenious machine which slips the laminations into the potential coil, one at a time, through the center and over the top, so that the coil is practically enclosed in the one-piece lamination. From the laboratory comes a red bag full of small metal pieces which are added to the assembly. The lead seal is broken and the pieces in the bag are ready to be installed. We'll have to have a closer look to see the wide limit load shunt which the lab man brought in the sealed bag. 2 pieces and a spacer constitute the shunt. It is simple looking, but it assures accurate performance at both light and heavy loads. Each shunt is carefully prepared in the laboratory before it is brought to the element assembly line. Then further down the line we see the riveting of the current coil laminations to the potential laminations. They fit together so closely that the magnetic flux between them is practically unimpeded. Rigid mechanical construction is essential in the electrical element. Definite, unyielding alignment assures unchanging calibration. All connections in the element are soldered by a special method which concentrates the heat just where it's needed. The lead wire is placed in contact with the terminal on the bench and the terminal of the element. The tool in the girl's hand isn't a conventional soldering iron. It supplies an electrical current, and contact resistance generates heat at the exact point which assures a solid connection every time. After a preliminary inspection, the electric elements are impregnated with an insulating varnish and placed in an oven to bake for several hours. While they're baking, let's look in on some other phases of meter construction. The shaft and disc and bearing assembly, for instance. The rotating element is extremely light in construction, yet when its weight is concentrated on the tiny, rounded pivot of cobalt tungsten, the pressure exerted on the jewel is equal to 70 tons per square inch. Now, 70 tons of pressure is a lot of weight for a bearing surface to hold, so of course the sapphire jewels are very carefully chosen. The crystal structure of the jewels is known, so that they can be placed to present their most wear-resistant face to the tremendous pressure. Each jewel is carefully inspected, measured for depth, and classified. It must meet rigid specifications of size, shape, and quality, before it is sent to the section where the many delicate operations in jewel setting are carried out with the utmost precision. In this next operation, the outside dimension of each individual jewel determines the size and depth of its mounting by a clever pantograph arrangement known as the jeweler's rest. The jewel is placed near the top of the machine to act as a model for its own mounting. The cut is made, and then the jewel is spun into the mounting. Then, of course, each mounted jewel is thoroughly inspected under a high-power microscope. This inspection operation is very complete, and the inspector has been specially trained for the job. Each cobalt tungsten pivot is set into the pivot blank in this manner. First, spot and form the blank, drill the hole, space for length, then insert the pivot and press into the blank. In the next operation, the pivot is checked for overall length. When the length is right, the little light on the left flashes on. If the pivot is too long, the light doesn't light. If too short, a buzzer sounds. They all check. So they are set in this geared fixture. When the fixture is placed in the lathe, each pivot revolves several times for every revolution of the fixture. The special polishing compound produces the final high brilliance of finish so essential to satisfactory performance. When this operation is completed, the glistening pivots are inspected under a high-power microscope. The fixture is so arranged that the pivot can be moved in front of the microscope or rotated into any position. Many rotating elements are mounted on cobalt tungsten ball bearings. In this type bearing assembly, the ball is placed between two sapphire jewels. Each tiny bearing is given a microscopic inspection. If you look closely, you will see one of the tiny balls slide into the inspection groove. Here's a speedy operation, making the top bearing pin assembly. The blank is pieced, spotted, drilled, and the pin is set. The pivot blank is turning at a speed of 10,000 revolutions a minute during this operation. The hole which is drilled is only 17 thousandths of an inch in diameter. Next, the top bearing pin is inspected in a projection microscope. The shadow of the pin is so greatly enlarged that any error in construction or alignment will show up clearly. Here the disc, which has been accurately punched from special scratch-free aluminum stock, and the shaft are fastened together in a die casting machine. The molten metal, which is forced into the joint, hardens almost instantly, making the shaft and disc into one solid piece. Skill of a high order is necessary here, where the rotating element is straightened so that it moves freely between jeweled gauging points. It will run true and accurately in the finished watt-hour meter, driving the train of gears which add up the revolutions of the disc and divide them by the proper factor to give the answer in kilowatt hours. No part of a machine is more important than its gear. Every gear which is used in the register train of the wide limit watt-hour meter is inspected before it is placed in the automatic machine which stakes it to its shaft. Other gears are set to shafts on a jeweler's lathe. The shaft size determines the hole size. The operator checks to be sure that the gear is straight, and then the assembled gears and shafts are placed in a tray for a cleaning dip before they are taken to the register assembly line. Here the gears, front plate and ratio plate are assembled and checked by dexterous fingers and accurate machines. Notice that the front plate is covered with paper to prevent scratches and mars on the finished face during succeeding operations. The train gears are placed and the back plate is set on. Note the sure, easy movement of the operator's hand. Here, the partially assembled register is placed in a press. The pointers are deftly set on, and presto, the gear shaft ends and pointers are one, held in a firm pressure bond. Now, with the nearly completed register set in a fixture, the bearing plate is lined up and tightened. Next, a thorough and accurate inspection. The end play is checked and the gears are twirled to test the freedom of gear movement. No binding wanted here. At the end of the line, 20 registers are placed on the checking device at once. A switch is turned and all the pointers move together, telling us that the registers all have the same ratio. Now, as soon as the operator has stamped her initial on each register, the box of 20 will go to the final assembly line. We're going there too, but first we'll go to another building and see how the Alnico magnets are made. And here we are. These men are making molds for the Alnico magnets. Notice how thoroughly the prepared sand is packed into the metal form. Then it is pressed, turned over and vibrated. A compressed air vibrator does the trick. This piece is 1/2 of the completed mold. Each mold will form 12 magnets. An electrically heated baking oven converts the crumbly sand forms into hard, strong molds. Steel magnet bases are placed around the outside of the assembled mold. The extruded tips on the bases assure a firm bond between the magnet casting and the base. The Alnico itself is a meticulously blended alloy of cobalt, copper, iron, nickel, and aluminum. Separate balances weigh each raw material precisely. These materials are melted together approximately 100 pounds at a time in a high-frequency induction furnace. Each time the alloy is poured into the ladle, a parametric check is made to be sure that the Alnico is within the closely held temperature limits for casting. Quickly, the operator swings the ladle over the spinning mold and pours it in. Centrifugal force acting on the molten metal forces it solidly around the extruded tips of the base, making the Alnico poles and base one piece. The spinning molds move on through the machine. While still hot, they're removed from the machine and placed in a cooling chamber. Later, the magnet castings are broken from the mold. At this point in the process, samples are taken for a complete check of quality. Alnico cannot be cut by ordinary methods, so after the excess sand has been removed, the tops of the castings are cut off with an abrasive cut-off wheel to approximate dimensions. Then 150 of the castings are mounted in the magnetic chuck of a face grinding machine. A fine, smooth finish is produced with dimensions from the bottom of the base to the top of the pole pieces very accurately maintained. A shunt composed of a temperature-sensitive material which compensates for Class 1 or Unity power factor temperature errors is placed in the shunt support and temporarily held in place by the friction spring for the full load adjusting screw. Then the shunt support is solidly welded to the magnet base in a thyratron-controlled welder, and the temperature-sensitive shunt is clamped firmly between the pole pieces and the shunt support. Steel for making the magnet yoke is fed in here. Thoroughly cleaned in its personal washing machine, and then goes on to a series of bending and broaching operations. The completed yoke emerges here, all machined to make a close-fitting joint with a magnet base. Now the yoke and magnet are welded together. The one-piece, all-welded construction is assurance that the air gap will remain absolutely constant. Now for heat treatment. The temperature cycle of this heat-treating oven furthers the process of producing a stable magnet. Next, the magnet is bonderized to prevent corrosion and to provide a better surface for adhesion of enamel. As you see, the bonderizing is done before the magnets are removed from the heat-treating oven conveyor. Here the fine characteristic of Alnico, its high coercive force, becomes a momentary handicap because it's just as difficult to magnetize in the factory as it is to demagnetize in the field. A Thyrotron tube-controlled surge of current completely saturates the magnet. Here, an electric eye controls the synthetic varnish spray. No magnet, no spray. This corrosion-resistant coat is applied before the magnet enters the oven for another stabilizing baking treatment. Later, the magnet assembly is placed in position to act as the damping magnet for a meter. By observing the speed of the meter stroboscopically, the operator adjusts the magnet strength to the correct calibration. A number proportional to the magnetic strength is stamped on the top of the assembly. Next, it is transported to the station for the insertion of the full load adjusting screw, which provides an adequate range of full load adjustments. Then, after further temperature stabilization treatment, the magnet assembly is started on its way to the final assembly line. The final assembly line is, in effect, the most complicated and smoothly functioning machine used in the production of the wide limit watt-hour meter. The care that has been taken in manufacturing all of the many parts serves the double purpose of making a superior article and contributing to the smooth operation of the assembly line. Electric and ratchet screwdrivers and wrenches are used extensively all along the line to start many operations. But the final tightening is always done by a man with a hand tool. Thus, the touch of an experienced workman, a man who through years of practice has acquired the feel of a correctly fitting part, makes an important contribution to the finished meter. Each succeeding operation is, in effect, a check on the previous one. That is, all operations are interdependent. This piece must go on perfectly or the next one won't. All similar pieces must be interchangeable, must be made with great accuracy and uniformity for an assembly line such as this to function at all. A strong vibration and air blast fixture is conveniently at hand to avert the possibility of foreign material getting into the growing meter. Note the clever way the operator puts the washers on the screws. The washers are moved over a slot. The operator inserts a screw with each hand, and then she slides the screw and washer out together and quickly places them in the meter. All of the operators on the final assembly line have been carefully chosen for special natural skills. Finger dexterity and other tests have been used for many years at West Lynn to select employees and to determine the special capabilities of the ones selected. This ingenious who's-it, the screw-holding screwdriver, makes possible the quick and accurate positioning of screws in tight places. Particular abilities, such as those required for inspection operators, are determined by appropriate tests. Regularly spaced rest periods help to eliminate fatigue, and the excellent working conditions and friendly atmosphere of the West Lynn plant are further assurance of continuous, accurate workmanship. The worm gear of the rotating element is carefully brushed before it's placed in the meter. All along the line, precautions are taken to keep every part of the meter scrupulously clean and free from dust. The special materials and alloys used in the I-30 meter are the result of years of development and research. The fine workmanship and manufacturing methods as shown in the operations of the final assembly line are no less a development of research. Each movement of each operator has been carefully studied to make the work easier and at the same time to produce a superior product. In this fixture, the Alnico magnet is brushed and cleaned under a strong blast of air. Materials, workmanship, and methods of the quality employed here at West Lynn have made the wide limit watt-hour meter one of the most outstanding examples of dollar value in all American industry. This complex device, which is made with instrument precision, sells for no more than many simpler, more familiar objects. Rotating element in the fixture of a projection microscope. The mesh standard is on the left. Now we have reached the end of the assembly line proper, but before the meter is complete, it must go through a series of complicated tests. First, the meter insulation is subjected to a high potential test to show up possible electrical weaknesses. This new automatic testing equipment makes possible accurate calibrations and adjustments of meters. The ones that pass this test are right. At the far end of the test panel, the meter is calibrated stroboscopically at full load. Here, directly before us, the meter is mounted and carefully checked by a special photoelectric testing equipment through the use of a triple rotating stander for accurate performance under light load, full load, and lag load. The colored scales give the limits to which the operator works. The last visual inspection is made by an experienced operator. The cover is put on and the meter is ready for use. This is the wide limit watt-hour meter of today, starting its quarter-mile conveyor ride to the shipping room and the customer. And the toughest customer to please is our own engineering laboratory. Each day, this laboratory takes a number of meters out of production and checks them for calibration and mechanical perfection. Weekly, a large group of meters are put through an additional series of rigorous tests. They're plunged into the Arctic winter of an artificial Klondike, the steaming heat of a laboratory tropic jungle, then to the burning dryness of a man-made desert. All these things to assure uniform performance under all types of weather conditions. On extensive racks, well over 1,000 meters are running on accelerated life test under simulated service conditions. Some of these meters have run at speeds so far above normal and for such long periods of time that their operation is equivalent to 100 years of actual service. Just as individual meters on test have proved their stamina and worth by giving the equivalent of a century of service, the GE meter department has proved its worth by over half a century of actual development, half a century of continual improvement of meter engineering, design, and manufacturing methods. The meters you've seen in construction today are made not only with fine workmanship and materials, but each meter has in it something of the men who developed these earlier models, something of their years of toil and effort. Men of unquestioned, outstanding engineering ability have devoted their whole working lives to the development of the wide-limit watt-hour meter. It is on such firm foundation that the excellence of the modern meter is built. But what of the meter of tomorrow? What will it look like? What will it be like? No one can show you, no one can tell you what it will be like, but we can show you where it will come from. Test men, student engineers, recent graduates of engineering colleges who are today still learning will in 1960 design that meter of the future, just as their predecessors for 50 years have wrought the engineering improvements culminating in the meter of today. The methods department will, as it did yesterday and is doing today, devise the processes and machines which will be used in manufacturing the meter of 1960. The range of dexterity and adaptability tests will be further extended, so the workers who make and assemble the parts of the meter of tomorrow will be even more perfectly fitted for their individual operation. Apprentices now learning their trade will be the shop foremen of tomorrow, the men who will employ every manufacturing innovation in making that meter of 1960 better and less expensive. Most significant of all, the meter of 1960 will be the result of many more years of improvement than exist in the highly efficient and accurate watt-hour meter whose manufacture this picture portrays, and it will come from an even more voluminous file of knowledge and even broader background of experience. Just as the first Thomson meter and its successors led the parade yesterday, just as the present wide-limit meter leads today, so will the General Electric watt-hour meter of the future be leading tomorrow.